Hello everyone, this is Dan Alistarh from IST Austria, and today I'm going to talk about memory tagging, which is a new synchronization technique for scalable search data structures. This is joint work together with Trevor Brown, who's going to join us a bit later in this presentation, and Nandini Singhal, who was an intern at IST Austria during most of this work. So in our paper, we start from a fairly basic question, which is what's the minimal amount of synchronization needed for a correct and efficient search data structures? Obviously, we're not the only ones to be answering this question. So there's several answers we can get from by looking at the literature, for instance, fine-grained locking, or all of these very elegant fine-grained lock-free data structure techniques. And then also HTM and hybrid TM are trying to answer similar questions, basically trying to trade off expressivity versus efficiency versus guarantees for different types of data structures we might want to implement. Perhaps the slightly novel angle we have in this paper is that we're looking at data structure techniques from the point of view of the minimal amount of synchronization that's needed for data structure correctness, but also how to implement this efficiently at the level of hardware. So hopefully that's going to become a bit clearer as we build more examples. So a very basic example behind the motivation for our technique comes from the Harris-Michael lock-free list design. So remember that this basically starts from a sequential linked list, where one of the main challenges is that we want to prevent concurrent insertions while we're removing nodes. So in this example here, we could have thread P, which is trying to delete node C, but concurrently, thread Q could try to insert element D, which would come right after C. So one issue here is that if Q's insertion is interleaved in an unfortunate manner with P's delete, we could end up with D being inserted after C, and then it sort of just disappearing from the data structure, while this should obviously not happen. So the solution proposed by this technique is to mark logically deleted nodes, such as C, by modifying their outgoing pointer, basically their next pointer. So basically, in this way, we would mark C as logically deleted first by marking its next pointer, and then actually swinging, making the corresponding pointer swing. So what this ensures is that no thread may successfully insert nodes after a logically deleted one. So in particular, Q's insert here would fail if it is trying to do this after a logically deleted node. Marking is an elegant solution to two problems. One, the fact that we're marking nodes in order to signify that they're logically deleted, but then also it ensures that no further nodes can be inserted after such nodes. However, one can ask whether marking is synchronization optimal in the sense that it uses the least amount of synchronization needed at the hardware level. So if we look at this failed insert example, we might see that there are these corner cases where this might not be the case. So in particular, we could have the following interleaving. Q first reads the next pointer of node C, and so far this hasn't been marked, so it doesn't see anything fishy going on. Then P modifies via compare and swap this next pointer, invalidating Q's copy, the copy present in Q's L1 cache. And then after this, Q unsuccessfully attempts to update C.next. So notice that in this case, this compare and swap would fail because it's trying to swap against an invalid value. However, this still causes cache traffic because Q still needs to bring in the current copy locally, compare against it, and so on. Okay, so this extra cache traffic by Q is unnecessary because Q's cache already knows that the line is invalid since it was the one doing the invalidation. And then therefore the operation could fail immediately locally. So the intuition behind MemTags is that it would be nice if we could leverage this information present in the local cache in order to render data structures more efficient. So memory tags allow the programmer to mark memory locations during a data structure traversal and to later check, validate that these locations have not been invalidated at the cache level since the last tagging step. So in particular, we allow the following operations: add tag onto a node, which just puts a tag onto a node. This will be tracked from now on against invalidations. Then remove tag sort of removes the corresponding tag from a node. Then validate and swap, which works pretty much the same as compare and swap. It validates all given set of tags. If these validation is successful, so none of these tags have been invalidated, then it atomically changes the value of a single location. And finally, the most complex such operation is invalidate and swap, which first validates all of the thread's local tags. If this is successful, then it invalidates tags at a given set of locations at all other threads or cores. And then finally, if this is also successful, then it may update the value at a single tag location. So this is just a slightly more complex version of compare and swap, or validate and swap, which allows you to, in addition, invalidate a subset of the nodes remotely. Okay, so what we show in the paper is that tags can be implemented efficiently on top of L1 cache for reasonable messy type protocols. And then we show that, first of all, they are useful to implement efficient marking, which is maybe not that surprising. But then what we also notice is that they enable a new and interesting hand-over-hand tagging technique, which we actually believe is a sort of more noteworthy result. So to illustrate hand-over-hand tagging, I'll hand over to Trevor. So enjoy.
Okay, so now I'm going to discuss the primary application in this talk, which is the use of MemTags not to design a new data structure, but to accelerate a state-of-the-art concurrent search tree, specifically an A-B tree, which is a generalization of a B+ tree, a tree that's sort of more cache-friendly because it has fat nodes with lots of keys. Specifically in an A-B tree, when there are no ongoing updates, non-root nodes contain between A and B keys, where A and B are constants, you're allowed to choose, subject to some constraints, and all leaves have the same depth. This is similar to a B tree or a B+ tree. Now these so-called balance invariants can be violated during updates, which allows us to be a little bit more concurrency friendly. But when there are no updates ongoing, these invariants hold strictly. Okay, so what we're going to do is we're going to take an existing implementation of an A-B tree that uses the LLX and SCX synchronization primitives, and we're going to try to transform it. So as a fast code path, we modify it to use MemTags instead of LLX and SCX, and if we fail to make enough progress on the MemTags fast path, we'll fall back to the LLX and SCX-based slow path. Okay, but what are LLX and SCX? Well, these are high-level synchronization primitives that operate on nodes directly. And what's a node? It's a collection of fields. So what are the semantics? Well, an LLX on a node returns a snapshot of the fields of that node, an atomic snapshot. And an SCX atomically changes one pointer, so you're able to specify which pointer you want to change and what you want the new value to be. And you're also able to specify a set of nodes that you would like to be finalized, and it will finalize those nodes, preventing further changes to them. This is similar to marking, really. And SCX will do these two things atomically only if no node has changed since the thread performing the SCX last performed LLX on that node. So the key usage pattern is going to be, we typically perform a sequence of LLXs. I'm showing that in these blue nodes on the right, and the return values of these LLXs sort of paint a picture of the data structure for you. So these sort of tell you what a subgraph of the data structure looks like, or at least you think it looks like if there are no concurrent changes. You select a subset of those nodes that you LLX that you you'd like to replace and finalize. You create new replacement nodes, and you use an SCX to atomically finalize those old nodes, remove them from the data structure, replace them with the new nodes that you created, and do all of those things only if none of the blue nodes have changed since you LLX'd them. So this helps you do atomic data structure updates. And this design pattern is what the LLX and SCX-based AB tree does. So how does its insertion work more specifically? So here's a simple two-level AB tree. Let's demonstrate the insertion of a key C. So suppose a thread P wants to do insert C. The first thing it does is it finds a node that it would like to modify, the node where it wants to insert, as well as its parent P. Then you perform an LLX on the parent P, and an LLX on the node N that's going to be modified, and the LLX will return a special value if either of those nodes are finalized. So if either of those nodes are finalized, and we're going to finalize things when they're deleted, so finalizing and deletion are going to be synonymous. If either of those nodes are deleted or finalized, we have to retry from step 1. Okay, if not, we get to proceed to step 5, where we use the data that was read and returned by these LLXs to create a new leaf that contains the keys of the old leaf plus the new key we're trying to insert, and we do an SCX to finalize the old leaf and replace it with this new leaf that we created. Now, I want to point out that deletion is just the inverse of this case. All the steps are the same, except we replace the leaf N with a new leaf containing one fewer key instead. Okay, that was how we insert if the leaf was not already full. What if the leaf is full? So what if we'd like to insert Q into N here? Well, we actually have to create maybe some new node. So how does this work? Well, we LLX the parent, we LLX the node we'd like to modify, and then we create two new leaves that evenly share the keys of the old leaf as well as the key that we have inserted, Q, and we have to create a new parent to link those two new leaves in. So we create a new singleton parent with one key and two child pointers, and we replace atomically the old node N with this new parent containing a single key using SCX. We finalize the old node N. Now, I want to point out that these leaves are at different depths now. We have some leaves at different depths, so this is no longer a strict AB tree, so we actually have to rebalance to fix this. And I won't describe all the rebalancing operations, but I'll describe one of them briefly. So this rebalancing operation is called absorb sibling. This applies when a node and its sibling could be combined. All of their keys could fit in a single node. And we do what the operation sounds like. We take these two nodes and combine them. And in order to do this, we create a new node that contains the combination of the keys of both of those previous nodes. And also, of course, the parent is going to have one fewer child pointer now, because instead of two nodes, it's pointing to one of the single replacement node and one fewer keys. So we're going to have to modify the parent as well, and we won't be able to do all of that in a single pointer change, so we have to replace the parent with a new node as well. So we can do all of this with a single pointer change, so we can implement it with SCX. So we create a new node, a new leaf, a new parent, and we use an SCX to atomically finalize these three nodes and replace them with these two new nodes. Okay, so this follows the same basic design pattern as all of the AB tree operations. Change a single pointer and atomically replace one or more nodes with one or more new nodes. Okay, so how do we take that implementation and replace its usage of LX and SCX with MemTags? Well, we sort of have to emulate the behavior of LX and SCX. So emulating the behavior of LX is not particularly hard. It returns a snapshot of a node. We can fairly easily replicate that with tagging because if we tag a node before we read it and then we validate it after we read its contents, well, the validation will succeed only if that node hasn't changed since we tagged it, i.e. if all of the values we read from the node represent an atomic snapshot of the contents of that node. So that's easy. SCX is not so easy to replicate because it not only changes a pointer like we do with VAS or IIS, it also finalizes nodes, and replicating that capability is subtle. Well, how does SCX do it? Well, the existing implementation of SCX uses marking, really, to implement finalizing. And, of course, that means it has to atomically set the marks of a whole bunch of nodes, one mark in each node that's being finalized. If we were to use marking like they do, we would have to use VAS or IIS to set each mark in each finalized node. We have to do lots of VASs or IISs. This is inefficient, and this is not what we want to do. We want to be able to perform a single VAS, a single IIS to accomplish a data structure update. But if we didn't use marking, then it's not clear how we could tell whether a node is deleted. We can't simply look at the node and look at its mark to see if it's been deleted to disambiguate. Okay, well, here's a naive approach that actually allows us to get away from using marking. What if we just tagged all of the nodes on a root to leaf path whenever we performed an update or a search? So suppose we wanted to do an insert of C, and we tagged every node on the search path to C, and then finally, instead of doing an SCX at the bottom, we would just do a VAS. We'd create a new node, do a validate and swap to replace the old node with a new node. Just a validate and swap instead of the SCX. So how does this replace marking? Well, if this VAS succeeds, we know that none of the nodes that we have read, none of the nodes in this path have changed at all since we read them. And in order for any of the nodes on this path to be deleted, some pointer that we read as we followed pointers along this path to reach the final node, some pointer must change in order for some node on this path to be deleted. Well, that would necessitate a change to one of these nodes, so that can't have happened if our VAS succeeded. So full path tagging actually makes marking unnecessary. Now, unfortunately, full path tagging has some problems. There are a lot of tags, and this makes us susceptible to contention on the entire path, even if it would be perfectly fine while we're sort of navigating some lower part of the tree for some update to happen in some upper part of the tree, on some upper portion of our path concurrently. That'll cause us to fail our validate and swap here, possibly unnecessarily. So you might wonder, could we untag some of those nodes before our final validate and swap in sort of a hand-over-hand fashion, like you might do hand-over-hand locking? Well, here's an observation about A-B tree operations that'll help with that. So if you think back to the A-B tree operations that I showed, you change one pointer, and that modifies a node, right? The node containing the pointer that you're changing is modified. But in doing so, you also sometimes delete and replace some other nodes. And so you change one node, and you replace possibly that node's child and maybe some of its grandchildren. But no A-B tree node operation ever deletes a great grandchild. So what does this tell us? This tells us that at the moment a node is deleted, it's deleted because its parent or grandparent changed. A pointer in its parent or grandparent changed. So this gives us some hope that maybe we could detect concurrent node deletion by tagging the parent and grandparent. Okay, so here's an idea. What if we maintain tags on the last 3 nodes that we traversed, and every time we tag a new node, we validate to make sure that the nodes that we've currently have tagged are all valid, none of them have been deleted, and whenever we sort of tag a 4th node, we untag the oldest node along the path that we've traversed, so we keep 3 nodes tagged at all times. Well, does this work? Well, it turns out it doesn't. Here's a counterexample that'll explain why, and then we'll fix it. So suppose thread P wants to insert A into this tree. It'll start tagging and validating as it goes. So we tag, validate, tag, validate, tag, validate. And suppose all of these validations are succeeding. Tag, validate. Now that we've validated a 4th tag, we no longer need the earliest one, supposedly. So let's untag the first one, and we'll tag the next one and validate. And now, suppose we're poised to do, we've created our node that we want to insert, and we're poised to do a validate and swap on this pointer. And right before P does that validate and swap, it sleeps. It's context switched out. And concurrently, another thread, Q, does an absorb sibling operation that is going to do a VAS on this pointer. So this pointer is a pointer in the root node. So Q is going to change the root node. So if the root node were tagged, P would notice that change. That change would cause P's next validate and swap to fail. But of course, it's not tagged by P right now because P untagged that location. Okay, so what will this absorb sibling do? If you think back to an absorb sibling, it ends up replacing a child and 2 grandchildren. So suppose that these 2 nodes are replaced by new nodes. So GP has actually been replaced by a new node, which we'll call real GP here. Why is it called real GP? Well, N actually has a new grandparent now. This is the new real GP, and this is not tagged. P has not tagged that node, so P actually can't track any changes to that node. So as a result, P's changing can now miss changes to the real GP, so it can't detect the deletion of n, p, or gp. Okay, so you might have some intuition here about why this is a problem, but let me directly show you why something bad can happen here. Suppose that q now does another absorbed sibling that changes this pointer. So it's changing a pointer in real GP, and that absorbed sibling is going to replace these two nodes with new copies. So at this point, the node P that thread P is going to modify with its VAS is deleted. So when P subsequently wakes up and does a VAS, it's going to succeed because that node has not changed. None of P's tagged nodes have actually been changed directly, and yet they're all deleted. So P is going to insert a new key into a deleted part of the tree. Okay, so that's wrong. Okay, so that idea doesn't work. But this is where invalidate-and-swap comes to the rescue. So replacing validate-and-swap with invalidate-and-swap here actually solves this problem, because suppose we're at the point where P was sleeping just before performing an invalidate-and-swap instead of a validate-and-swap. And absorb sibling here by Q is going to do an invalidate-and-swap instead of a validate-and-swap. Okay, so that invalidate-and-swap, when it replaces these two nodes, it's going to invalidate them. So what this means is P's tags on these two nodes are going to be invalidated. So at any time in future, when P wakes up and decides to try to do this invalidate-and-swap on this pointer, that IAS is doomed to fail, as it should be. Okay, so this fixes the problem. Okay, so let me very briefly show you some experimental results. So of course this was a hardware proposal, so we had to implement it in a simulator. So we used the Graphite multi-core simulator to implement a 32-core tiled processor. We have private 32K L1 caches and a shared L2 cache. I believe it was 256K. We used the MESI protocol, and we implemented MemTags in the L1 cache, so that's where all the tagging takes place. And I'll just show you one of the many experiments that we ran. If you want to see more, then I encourage you to take a look at the paper. This is a simple test on the synthetic microbenchmark on the AB tree. And here you can see we have the hand-over-hand tagging AB tree versus the original LLX and SCX variant. And you can see it actually makes an appreciable performance difference, the use of this hand-over-hand tagging. You might wonder why. To cut to the chase, it comes down to cache misses. Okay, so with that, I'll wrap up. Thanks for listening to the talk, and I encourage you, if you're interested for more details, to take a look at the paper.